Okay, so we're going to go ahead and start this section 3.3, which is kind of a big section conceptually. Okay, this is where we are moving from degree measure to radian measure so that we can get nice graphs of these trig functions on an XY axis. Okay, another way of defining trig function values is what we're looking at today. Okay, so you may remember this formula from section, I believe, 3.2. Again, this is a formula I would give you, but you need to know how to use it. Okay, remember, theta is our angle measure in radians. Okay, S is the arc length, and then S is also in the units of the radius r. Okay, so our question here, or one thing I guess I want you to be able to pick out is that if r equals 1, okay, if we have our radius value set at 1, then notice what happens. Then that means S is equal to theta, okay, or our arc length measure is equal to our angle measure in radians. Okay, and this becomes very, very helpful in calculating our x and y values, or our points on the graph, right? So if we were to pick a point and label it xy, right, this is going to help us be able to define these values in terms of our trig functions. Okay, so let's see. Question: on the unit circle, what is the length of the radius? Or another way to pose the same question is, what is the value of r? So on a unit circle, our r value is going to equal 1. And the reason that is when we first started defining trig function values, remember we talked about how it doesn't matter which point on the terminal side that we pick to drop down and draw our angle with, right? All of the points that we choose, when we drop it down to a 90 degrees and come up with our triangle, we would always end up with the same trig function values. So especially when we chose our quadrantal angles, right? So like if I think about this on an axis, right? When I thought about quadrantal angles, so like 0 or 90 degrees or 180 degrees or 270 degrees, right? We always chose the easiest radius length, right? Just to make our lives easier. Okay, so that's what this is summing up down here. This is saying, since it doesn't matter which point we pick on the terminal side of an angle to evaluate the trigonometric functions, and basically to make our lives easier, right, we want to pick the point that makes r equal 1, right? Because if we can go out a specific distance of 1, right, then we get a lot of nice values, right? It's easier. We don't have to worry about simplifying and reducing down and all these things. Okay, the other thing that's really great is we can define these trig functions for the radian measures of an angle as follows. Okay, if we know that r equals 1, here, what this is saying is, hold on, sorry, my computer's going a little slow, so it's kind of jumpy. What we're saying is we can define these 2 points as the cosine of s and the sine of s. Okay, now how that helps us is if r is equal to 1, then we know that our arc length and our angle are equal, which means that we can also define this ordered pair as the cosine theta, sine theta, right? So let me just show you one example. Let's pick 180 degrees over here, okay? Let's pick 180 degrees. That's a half rotation, okay? So for example, if I am looking to find this point on a unit circle dealing with 180 degrees, I can now just simply calculate the cosine of 180 degrees and the sine of 180 degrees. Okay, cosine 180, sine 180, right? oh, my bad, and we're actually talking about radians. So instead of 180 degrees, I would define this as cosine pi, right, and sine pi, because we're talking about radian measures, right? Remember, a full rotation is 2 pi, so that means half a rotation, or at 180 degrees, this is pi, right? Okay, so what it's saying is I can define this little point just by figuring out what the cosine of that measure is and the sine of that measure, right? So let's think about that. What is the cosine of this point? Well, cosine, we calculate, we do x over r, right? Well, our x value at this point, if we're allowing r to be 1, right, we're going backwards -1, and then we put it over our radius, which is also 1. So that ends up being -1, right? Our sine value at this point, we calculate y over r. So our y value at this point is 0, right, because I'm not going up or down. And my r value is that radius of 1 that we've chosen to go out. So 0 over 1 is 0. So that's how we're getting this nice pretty point of -1, 0. Okay, so this was a nice quadrantal angle just to use as an example. But if we summarize this or write it generically, okay, down here at the bottom, what this is saying is, as long as we choose a radius of 1, we can create this unit circle to where we can define a point xy, where it's the point of intersection on the terminal side of the unit circle, okay, by simply finding the sine value, which again is the same as sine of theta, which is y over r. R we've defined to be 1, so what happens is it ends up just being y, right? So in other words, we can find sine theta, and that gives us our y value. Okay, similarly for cosine. Cosine, we get x over r. We've defined r to be 1, so that means our cosine of theta gives us our x value, which is what we just showed on that example above, where I ended up with the point -1, 0, right? And then we can find our tangent value by simply doing y over x, and then our inverses, same thing, just with the reciprocals, right? Okay, so now that we have that, what we can easily do is we can do what we did in section 3.1, which is to label our entire unit circle with radian measure. But now, using this, we can also define an xy point on that circle where each degree measure hits on its terminal side. So let me show you what I'm talking about on the next page. And I'm going to do my best to put this where we can see the whole circle, okay? I'm going to scoot it down just so I can read the print really quick though. Okay, it says, assume that the given circle is the unit circle. So when you see unit circle, we should be thinking that the radius is 1, okay? Anytime you see that, I'm going to write that even big up at the page. Unit circle means r equals 1. Okay, that's something we want to make sure that we know, okay? All right, so what we're going to do is identify the radian measure of each of the angles, okay? And then we're going to label the xy coordinates of the point of intersection on the terminal side of each angle. So what that means is we want to write each of these with its radian measure, but then we're also going to define this point for each and every angle, okay, where its terminal side hits the unit circle, okay? So again, the unit circle is just the circle that we get when we go out a radius of 1 and draw it all the way around, okay? All right, so let's go ahead and just review really quick how to label things with a radian measure. Remember, this is 0, right? Or you can think of it as 1 full rotation. 1 full rotation is 2 pi, right? And 1 full rotation is 2 pi, then that means that a half rotation, or 180 degrees, would be half of that, which is just pi. Okay, and we can use that same logic to figure out what 90 degrees is. If half of a rotation is pi, then half of that half rotation, or a quarter rotation, is going to be pi over 2. Okay. All right, so what that means is my quadrantal angles can be counted by pi's over 2. So this is 0, this is 1 pi over 2, this is 2 pi over 2, which then just becomes pi, and then this one down here is 3 pi over 2. 3 pi over 2, okay? All right, so we have those labeled. Now we want to go back and remember how we figured out what to label 30 degrees as, is we looked at 30 degrees as a fraction of 90 degrees, okay? So 30 degrees is 1/3 of 90 degrees, which means that in radian measure, it would have to be 1/3 of pi over 2, right? And 1/3 of pi over 2 gives me pi over 6. So then remember, we counted by pi's over 6. So this is 1 pi over 6. When I go another 30 degrees, this is going to give me 2 pi over 6, right? So I'm going to count by pi's over 6 for every 30 degrees, okay? And then I'm also going to reduce, because I want to make sure my answers are reduced. So this is 1 pi over 6. This would be 2, put my fingers over here. This would be 2 pi's over 6, right? But 2 pi's over 6 reduces to pi over 3. Okay, and then this is 3 pi's over 6. 3 pi's over 6 reduces to pi over 2. Let me go a little bit further. Now we have 4 pi's over 6. So 4 pi's over 6 reduces to 2 pi over 3. Right? We go to the next one, and that gives me 5. Can't get my fingers on here. 5 pi over 6. That does not reduce. Okay. And then we come down to 180, so this was 5 pi over 6. This is 6 pi over 6, which again reduces to pi. I go another pi over 6, that gives me 7 pi over 6. And then I come down here, this gives me 8 pi over 6. 8 pi over 6 reduces to 4 pi over 3. This would be 9 pi over 6, which you can see is already reduced. At 300, we're at 10, oops, that one will reduce. 10 pi over 3, or sorry, 10 pi over 6 reduces to 5 pi over 3, right? I forgot which one, that was 10, right? 10 pi over 6, so this would be 11 pi over 6. 11 pi over 6, okay? All right, so now we've labeled all of our 30 and 60 degree measures. The last one we have to do is 45. Remember, 45 was exactly half of 90 degrees. So if 90 degrees is pi over 2, then half of pi over 2 is going to be pi over 4. And then we can count by pi's over 4. So this is 1 pi over 4. This is 2 pi over 4, which has been reduced. This is going to be 3 pi over 4. 3 pi over 4, and then down to 180 gives me 4 pi over 4, which has already been reduced. And then this one's going to be 5 pi over 4. Oops, I wrote that wrong. 5 pi over 4. And then all the way down gives me 6 pi over 4, which again has been reduced. 315 is going to be 7 pi over 4. And then when we come up here, that gives me 8 pi over 4. And 8 pi over 4, you can see, has been reduced to 2 pi. Okay, now the reason I go through all of this instead of just labeling all of these from memorization is this is something I expect you to be able to do on a test. If I give you a blank unit circle, I expect you to be able to take all these degree measures and label them with radian measures. Okay, and now that we have them labeled as radian measures, now we can actually determine what that XY point is on their terminal side using our reference triangles. So I'm going to start with our 30, 60, 90 triangles. Okay, so when I look at, let's say 30 degrees, I want to think about this as a reference triangle. So I'm going to scoot this down just a little bit so I have room to write a reference triangle. If I want to draw a reference triangle up here, okay, And let's say this is my 30, the way I've written it anyways, right? This is my 30, then opposite my 30 would be my side that's 1, right? Opposite my 90 degrees would be my longest side, which would be 2. And then adjacent, or opposite my 60, I'll go ahead and put 60 degrees in here. Right? Opposite my 60 would be square root of 3. Okay? So again, remember, we can label these by looking at solely their x and y values. Okay? So if I want to label pi over 6 for this little xy point right here, right? What I have to do is calculate the cosine of 30 for my x value and the sine of 30 for my y value, right? And I mean, you could use the pi over 6. I'm just using 30 because that's how we have our reference triangle labeled. Okay, so cosine of 30, cosine is adjacent over hypotenuse. So adjacent is square root of 3 over my hypotenuse, which is 2. Square root of 3 over 2. And then sine of 30 is opposite over hypotenuse. So opposite 30 is 1 over the hypotenuse, which is 1/2. Okay, so now we have that labeled. Okay, we can also use this triangle to label our 60-degree measure, right? If we label our 60-degree measure, we would just be looking at this angle instead. Okay, so we can calculate this one by doing cosine of 60 degrees and sine of 60 degrees, right? So cosine of 60 is my adjacent over my hypotenuse. So adjacent is 1 over my hypotenuse, which is 1/2. And then my sine of 60 is opposite, which is square root of 3, over hypotenuse, which is 2. Square root of 3 over 2. Okay? Now, what I want you to notice is, excuse me, remember, because these angles add to 90, they're my coterminal angles, right? In other words, my cosine of 30 equals my sine of 60, right? My sine of 30 equals my cosine of 60. So really, once I know my 30-degree xy point, I could just take those two and swap them to get my 60-degree point, right? The other cool thing is, now that I have these 2 points, I should be able to label every other 30, 60-degree reference angle on my unit circle, because the value should stay the same. The only thing that should change is the signs. Okay, so let's look at doing that. Let's start with our 30-degree angle. Okay, here's a 30-degree angle, right? Because if I drop that down, that's going to be a 30-degree reference angle. If I go in this side, this would be a 30-degree angle, right? So it should have the same x and y, except if I look at this point compared to this point, this one should have a positive x and a positive y, right? We're going to the left, square root of 3 over 2, and then we're going up 1/2. If I reflect that over here, what's changing, notice I still have the 1/2 being positive because I'm still above the x-axis, but I'm going in the left direction for my x. So the only thing that changes from this point to this point is my square root of 3 over 2 becomes negative. So this becomes negative square root of 3 over 2, 1/2. So notice I didn't even have to go back to my reference triangle and relabel it with positive or negative numbers. Once I know this point, I should be able to reflect it here. Same thing reflecting it down. If I reflect my 30-degree angle downward, I should be able to label this 30-degree angle, right? Because now notice, reflecting it down, what's changing from this point down to my bottom point is now, instead of having a positive y, right, I should be going down and having a negative y. So that means my 1/2 is going to be negative. So square root of 3 is still positive. Sorry, square root of 3 over 2 is still positive because we're still on the positive x-axis, right? But now we're going down -1/2. Okay. And then the last 30-degree angle I can do is the 210 angle, or the 7 pi/6, right? And I can use just this ordered pair that's up here at 150. If I reflect this down, notice my x is still going to be negative square root of 3/2, but my y is also going to be negative because I'm reflecting it down, -1/2. Okay. The other thing that you can think of is once you have square root of 3/2 and 1/2, all of these points are going to be square root of 3/2 1/2. All you have to do is figure out what their signs are, right? We know that in quadrant 2 the x is negative. We know in quadrant 3 x and y are negative. We know in quadrant 4 only the y is negative. Okay. All right, so now that we've done that with our 30-degree angles, now we want to do the same thing with our 60-degree angles. Okay. I'm going to see if I can focus this just a little bit. Okay, that looks a little bit better. All right, so let's scoot this just a tad. All right, so here's my 60. So if I know this 60-degree XY point, I should also know this one. I should also know 240. I should also know 300. Okay, so I know they're all going to have a 1/2 square root of 3/2. I just have to figure out their signs. So when I take this point and put it in quadrant 2, what changes is my x value. My x value becomes negative because x's are negative in quadrant 2. So -1/2 square root of 3/2. Okay. When I put that point down in quadrant 3 for this 60-degree reference triangle, right, then now they should both be negative. So -1/2 negative square root of 3/2. See if I can get this just a little bit higher so I can see the whole unit circle, just barely. All right, and then for 300, when I take this point, put it in quadrant 4, remember only our y is negative. So now our x value of 1/2 is going to be positive, and our y is going to be negative square root of 3/2. Okay, so again, I know I'm like reiterating this 800 times, but this is the easiest way to do it, is once we know our 60-degree xy point, right, the point that's created by intersecting the terminal side to the unit circle, once we have that x and y coordinate, then we should be able to label every single 60-degree in each of the quadrants. Same thing with 30. Okay, so we use this one little reference triangle to get our 30-degree x and y values and our 60-degree x and y values, but in order to come up with our 45-degree, we have to use its reference triangle. Okay, so I'm actually gonna see, where can I draw that? I guess I can just squeeze it down in here. So if I wanted to draw a 45-degree reference triangle, right, then all of these would both be 45 degrees. So it doesn't really matter which corner you draw it in. And remember, a 45-degree triangle we label as 1, 1, square root of 2. So if we want to find this xy point where the terminal side intersects the unit circle, then I can find the x value by calculating cosine 45 degrees, and I can find the y value by calculating sine of 45 degrees, right? So cosine, remember, is adjacent over hypotenuse. So adjacent is 1 over square root of 2. So 1 over square root of 2. And then our sine is also, should be the same, right? Because even though we're doing opposite over hypotenuse, we still get 1 over square root of 2. Now I will say this, just because we're using the reference triangle, I'm fine with you leaving this ordered pair as 1 over the square root of 2. My math lab will have you rationalize the denominator. But on an exam, if you have 1 over square root of 2 written on your unit circle, I'm totally fine with that. Okay, just make sure if you do anything with that, like if I ask you in a separate problem, like not fill out the unit circle, but if I ask you in a separate problem, like find sine of 45, then I would definitely want you to go ahead and rationalize the denominator, okay? But for the purposes of filling in your unit circle, I'm fine with you just using these values and editing their signs for each quadrant, okay? So here x and y are both positive. If I look in quadrant 2, now my x is negative, so negative 1 over square root of 2, 1 over square root of 2. If I reflect that down over here, they're both going to be negative, negative 1 over square root of 2, negative 1 over square root of 2. And then the same thing over here at 7 pi over 4. Now only my y is negative. So 1 over square root of 2, negative 1 over square root of 2. And again, if you want to go ahead and rationalize these, you can. You're just going to get square root of 2 over 2. So depending on if you came in with any pre-calculus knowledge or you've attempted trig before, you may have memorized the unit circle values. I'm totally fine with that if that's how you learn best, but I really want to encourage you to try and just remember the first quadrant worth of x and y points, because if you can remember those ordered pairs, you should be able to label the rest of the triangle, okay? Oh, and then I forgot to do the easiest ones, the quadrantal angles. So at 0 here, right, or 2 pi, however you want to consider that, 0, it's also 2 pi if you do a whole rotation, right? Remember our radius value is 1. So if I want to label this point, this would just be the point 1, 0, right? 90 degrees here would be the point 0, 1. At 180 degrees or at pi, we already did that on our example earlier. This is going to be negative 1, 0, right? And down here at negative 270, if we label that point's going to be 0, negative 1. Okay? All right, so I do want to just point out really quickly that, you know, all these 30-degree angles that I have written in pink here are coterminal angles with all of the angles that I have written in blue, right? Because these are, they add up to 90 degrees. So I'm just going to write that up here. I know we've seen that before, but it's always a good thing to refresh. So I'm going to write here that the angle that's written in pink here plus the angle that I have written in blue is equal to 90 degrees. And if those two angles add up to 90 degrees, these two are coterminal angles. Okay? And remember what that tells us about coterminal angles is that the cosine of our pink angles is equal to the sine of our blue angles, and that the sine of our pink angles is equal to the cosine of the blue angles. Okay, so just a little refresher on that, because really that means that you only need to memorize the first two ordered pairs. If you can remember that 30 and 60 are coterminal, then they have the exact same x and y, just swapped. Okay? Okay, so now that we have all those values written down, let's see if we can use them. Okay, so if we look at this next page, the next page says find the trig function values for 0 radians. Okay, so if we look for 0 radians on our unit circle is here, I have it in the background, and 0 would be right here, right? So if we want to find the sine of 0, we're really just looking for that y value, which we can see here is 0, right? If we're looking for our cosine of 0, that's the x value of the point that we found, which is 1. And then if we're looking for our tangent, remember tangent is x over, or sorry, y over x. So our y value is 0, our cosine value is 1, 0 over 1 is 0. Okay, so I want to give y'all just a second, and I would like for y'all to try to find these inverse, my reciprocal identities here for 0, and then I also want y'all to try the next 3 examples here. Okay, so do these as practice, and then do these as practice. Okay, I'm going to give y'all just a minute to pause the video, and then whenever you're ready, go ahead and play it, and we'll see how you did. Okay? All right, so let's go ahead and see how you did. So when we're looking at our reciprocal identities, cosecant is the reciprocal of sine, right? So cosecant of 0 is the same as 1 over sine 0. So we do 1 over whatever we got for sine here, which was 0. And remember, when the 0 is underneath, it's undefined. Okay. Similarly for secant, secant is the reciprocal identity for cosine. Cosine of 0, we got 1, and 1 over 1 is 1. Okay. Cotangent is the reciprocal of tangent. We got 0 for our tangent value, right? And 1 over 0, again, if 0 is underneath, it's undefined. Okay. All right, and then to find the following, I wanted to go ahead and work these out just because I didn't want that negative to confuse you. Okay. Remember when we talked about negative angles, that just tells us what direction we're going from our starting point out here on our initial side, which is on the x-axis, right? So if we're going a negative measure, or a measure of negative pi, that just means we're going this direction pi units, right? This is the same as negative pi. So just going that direction. So whatever we're asked for these questions are the same answers we would get if they just asked us for positive pi, right? Because we end up at the same place. So let's look and see what they ask us for. They ask us to find, let's get this up. They ask us to find sine of negative pi. So remember, that's just the y value. Sine is our y, right? And the y value we get at negative pi would be 0. Okay. Then it asks us to find our cosine, which is our x value, right, at negative pi, which here is -1. And then our tangent value, which is our y over our x. So we have 0 over -1, which just gives us 0. Okay. So again, if you want to circle or box in or bubble your answers, that's what we should have gotten there. Okay. All right, so let's look at a few more. These ones are giving us our angle measure in radians. Okay, so we want to find the unit circle to find each of the following. So I'm going to go ahead and do the first one. Or actually, I'm going to do this middle one. I'm going to do the tangent of 9 pi over 4. So the tangent of 9 pi over 4, that tells me I'm going in the negative direction, which is clockwise, 9 pi's over 4. Now remember, pi over 4 was a 45-degree angle. Oops, where's my picture here? So this is the one I'm doing. It says we're going to find negative 9 pi over 4. Remember, pi over 4 is a 45-degree angle, right? That's these that are in the middle, perfectly in the middle, right? So this one, this one, this one, this one, right? And then also our quadrantals, okay? So this tells me I'm going to go 9 pi's over 4 in the negative direction. So I'm going to start here, right? Here's 1 pi over 4, 2 pi's over 4, 3 pi's over 4, 4 pi's over 4, 5 pi's over 4, 6 pi's over 4, 7 pi's over 4, 8 pi's over 4, 9 pi's over 4. So I'm hitting right here. So that's where I'm going to stop. So notice this is the same thing as just saying 7 pi over 4. So I'm just going to rewrite this. This is the same thing as saying we're looking for the tangent of 7 pi over 4. Okay, so now remember our tangent is our y value over our x value. Okay, so this is our y value over our x value for 7 pi over 4. So we're going to get our y and our x value from our 7 pi over 4 measure. So our y value, as you can see, is negative 1 over square root of 2, negative 1 over square root of 2, and our x value is 1 over square root of 2, 1 over square root of 2. And then once we have that, then we can go ahead and simplify, right? So this just means negative 1 over square root of 2 divided by 1 over square root of 2. So we can just flip and multiply. So we get negative 1 over square root of 2 times, if we flip this one, we get square root of 2 over 1. Those are going to cancel, and I'm left with negative 1 over 1, which is just negative 1. Okay, so I want y'all to go ahead and pause it for just a second and try number 1 and number 3, okay, as practice problems. See if you can figure those out, and then whenever you're ready, unpause the video and we'll go over them, okay? Okay, so let's see how you did. When you calculate sine of 4 pi over 3, 4 pi over 3 is a nice angle that we have defined in our here it is. Okay, that we have defined over here in our third quadrant, right? So all we have to do to find the sine of that angle is to look at its y value. So the y value here is negative square root of 3 over 2, okay? Well, on the next one, we're looking for secant. Secant is related to cosine, right? But it's the reciprocal property, or reciprocal identity. So this is the same as 1 over cosine of 11 pi over 6. And then remember, this is we get from the x value of that angle, right? So if we look up 11 pi over 6, which is down in our fourth quadrant, you'll see that its x value is square root of 3 over 2. And then when we flip and multiply by the reciprocal, we get 2 over square root of 3. Now, I do believe my math lab will have you rationalize the denominator, okay? So we are going to go ahead and multiply this by square root of 3 over 3. So our final answer will be 2 square roots of 3 over 3, okay? So don't forget to rationalize the denominator, okay? Okay. So now I want to show you a few examples of being able to calculate these radian measures on your calculator. So if you have your calculator, make sure you go ahead and pull it out. If you need to pause the video and go get it, that's fine. I'm going to show you 2, and then I'm going to have you try some yourself, okay? Excuse me. So I'm going to go ahead and calculate number 1 and number 3. So number 1 is sine of 3.42. Now, just when I'm looking at this number, I just see 3.42. Pretty much, you're going to assume that if no measure is given, like you don't see a degree symbol in there, then we're just going to assume it's in radians. Okay, so I'm just going to write that. Assume that if no measure is given, that our value is in radians, okay? So if you don't see like a degree symbol, we're going to assume it's in radians, which means when we use our calculator, we need to make sure that our calculator is in radian mode, okay? So again, my mode button is this one that says DRG, which stands for degree. And if I click on that, I have the option to choose degree or radian. So you can see I already have mine set in radians, so make sure yours is in radians if it's not already. And then all we have to do is type in sine of 3.42. So sine 3.42, I'm going to close my parentheses. and hit enter, and you can see that this comes out to be negative 0.27482 and some more stuff. Okay, your homework will tell you how many decimal places to round to. For these problems, I'm just going to round to 3 decimal places. Okay, so I identify that third decimal place, which in this case is a 4. Since there's an 8 behind it, I'm going to go ahead and bump it up and say that this is approximately negative 0.275 for my solution. Okay, and then I want to show you one that has an inverse, or sorry, not an inverse, I keep saying inverse, reciprocal identity. Okay, secant is the reciprocal of cosine, right? So I'm just going to rewrite this as 1 over cosine of 5.6041. Okay, because remember, we don't have these reciprocal identities on our calculator, right? So we have to make sure it's written in terms of sine, cosine, or tangent in order to be able to use our calculator for them. So I believe your calculator should be able to do this all in one step. So we're just going to type in 1 divided by cosine 5.6041, and then make sure you close that parenthesis so we know that's all that's in the denominator, and hit equals, and we get 1.28510, 1.28510, and some more stuff. And then again, I'm going to go ahead and round it just to 3 decimal places. So that third decimal place is a 5, and the number behind it is a 1, so we're not going to bump it up. So this is going to be approximately 1.285. Okay. All right. So I want y'all to go ahead and pause the video really quick, and I want you to try number 2 and number 4. Okay, number 2 and number 4, and then when you're ready, unpause it, and we'll go over it. Okay. Okay, so let's see how you did. For tangent, that's something we can just punch right into our calculator, and we get 1.07904 and some more stuff. And again, I went ahead and rounded it to 3 decimal places. So that one was pretty straightforward. When we look at number 4, first we have to turn this into a sine, cosine, or tangent identity, right? Because we don't have a button for cosecant. Cosecant is the reciprocal of sine, so I can write this as 1 over the sine of negative 2.7335. And now this is something I should be able to do in my calculator. Now if you have a very basic calculator, you may have to do this denominator first and get an answer, and then do 1 divided by whatever that answer was, right? Either way, you should end up with negative 2.5197 and some more stuff. And again, if I round it to the third decimal place, you notice this bumps it up to 0.520. And notice I did include the 0, because if they specifically tell us to round it to a certain number of decimal places, we want to make sure we include that in our answer. Okay? All right. So now I want to look at a couple of solving problems, and then I want to talk about the domain of our trig functions, okay, using our unit circle, and then we'll be done with this section. So first example we have here is it wants us to solve for the sine of s, or it tells us the sine of s is equal to 0.3210 for an s that's in this interval. Now when I see an interval that has a pi in it, this is pi over 2, sorry mine did not copy very pretty, but that's 0 to pi over 2. That means we're in radian measures, right? We're talking about 0 up to pi over 2, okay? So that means we want a radian measure as our answer, okay? Now pi over 2, I'm going to go ahead and just put this over here. Pi over 2 as radian measure, if we bring in our calculator, and when your calculator's in radian measure, if you use your pi button and divide it by 2, you're going to get 1.5707 blah 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 blah. So I'm going to say this is approximately 1.57. Okay, so what I'm hoping for is whatever answer I get, it has got to be between 0 and 1.57, because I'm actually solving for that s, right? And remember, s is equal to our theta measure when we're talking about the unit circle, okay? So I want to make sure that I get a number less than this, but bigger than 0 in order for it to fall into this interval that they're wanting my answer to be in. Now, to solve for S, I need to get rid of this sign. And we get rid of the sign the same way we always have. We use the sine inverse. So I'm going to do sine inverse of sine S. But if I do it on the left-hand side, I also have to do it on the right-hand side. So I'm going to do sine inverse of 0.3210. Okay? So you can see on the left-hand side, my sine and my sine inverse are going to cancel. And this tells me that S is equal to sine inverse of 0.3214. We've done problems like this before, right? We're just now doing them in radian measure. So we're going to go ahead and use our second function, which is where my sine inverse is located. And we're evaluating that at 0.3210. And that gives us 0.326785. 0.32678517 blah 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 blah. Okay, and I'm not really sure how to round this one. It'll tell you in your homework, but the way that I'm going to do it is based on just, you know, significant digits. So I noticed the number they gave me had 4 significant digits, right? So I'm going to go ahead and just round this one to 4 significant digits, which would be that 7. Okay, so we're going to say here S is approximately 0.3268. Okay, and I can go ahead and just circle that in, because notice I ended up with an S value that fell below 0 and 1.57. So if I think about this being the unit circle, right, that means I would have gone maybe, let's see, if this is a distance of 1.53, then maybe I went a distance, maybe my angle looks something like that, right? Okay. I do want to do an example really quickly. If you had, well, actually I'm not going to do an example, I'm just going to talk about it. So this was a nice sine one, right? If they gave you something like the cosecant of S equals 1.3210, something like that, okay? Remember, we would first have to get this into a sine equation, because we don't have inverse function buttons for anything other than sine, cosine, and tangent, right? So I would just take the reciprocal of both sides here. So if I take the reciprocal of this side, right, then it becomes sine S. And then if I take the reciprocal of this side, it would just be 1 over 1.3210. And then I could go ahead and finish working this out by taking the sine inverse of both sides. Okay, so I just want to mention that if they give you a problem that involves a reciprocal identity, make sure you take the reciprocal of both sides to get it into a trig function that we have a calculator button for, okay? All right, let's look at this next one. This one wants you to solve tangent S equals negative square root of 3 over 3 for an S in this interval. So notice this interval, again, it's in radian measures, and it's from 3 pi's over 2 to 2 pi. Well, I know where 2 pi is. 2 pi is here, right? And then this is going by pi's over 2, which is a quarter turn, right? So here's 1 pi over 2, 2 pi's over 2, 3 pi's over 2. So this is 3 pi over 2. So that means my S value has to fall somewhere in here, right? So this is also equivalent to 0, right? And this is equivalent to, if I do 3 pi over 2, 4.71, right? Or they could give me a negative angle, right? This is assuming that I'm going around this direction, right? This would be 4.71. So this would be any number higher than 4.71. But it could also be a negative value if we go this direction, right? So just keeping that in mind. So let's go ahead and look at solving this one. This one we can do the same way on the calculator, because tangent is one of our friendly calculator trig function buttons, right? So we can go ahead and do tangent inverse of tangent s is equal to tangent inverse of negative square root of 3 over 3. So that means that s is equal to the tangent inverse of negative square root of 3 over 3. And we can punch that into our calculator and we should get approximately negative 0.524. Okay, notice we get a negative. So that does mean we're going back down this way. So if we're going back down this way and we want it to fall into this quadrant, then remember, I went ahead and calculated up here, 1 pi over 2 is 1.57. So if we're going in the negative direction, this would be negative pi's over 2, which would be negative 1.57. So notice negative 0.5 is falling below 0, or between 0 and negative 1.57. So we are okay. That falls in our area. We have no issue. The other thing I want to point out, and I don't know if this would be easier or harder, but this actually is a friendly angle, right? When I see square root of 3 over 3, I'm automatically thinking this is a 30-60 triangle, right? Because I'm used to seeing square root of 3. This is what I get after I rationalize the denominator. So had I not rationalized the denominator here, what this is saying is that tangent s is equal to negative 1 over square root of 3, right? And that's something that I can easily figure out what s would be, right? Because tangent is opposite over adjacent. We already know it's down here in quadrant 4. So in quadrant 4, we know that our opposite side is negative 1. We know that our adjacent side is square root of 3, right? And our angle that's opposite the 1 is a 30-degree angle, right? Or in other words, a pi over 6 in radian measure, right? So if I want to figure out what this angle measure is right here, right? This is 2 pi. And notice I'm 30 degrees shy of making it to 2 pi, or in other words, I'm pi over 6 radians short of making it to 2 pi. So I can just take 2 pi and subtract pi over 6. This is something you could do on your calculator. You can just get a common denominator, which would be 6, right? So if I multiply this one on top and bottom by 6, I get 12 pi's over 6 minus pi over 6, which gives me 11 pi over 6, which is my radian measure, right, for that same angle, okay? So there are two ways to work this one, just depending on if they want to you to have a decimal approximation of the radian measure, or if they want an exact with the pi in there, okay? So just a couple of ways to work it. All right, the last thing that I want to talk about really quickly is our domain of these functions. Okay, so when you see the word domain, what you should be thinking in your brain is all possible inputs. Okay, in other words, how far left to how far right, okay? Do we have allowable inputs? Okay, so when we talk about domain of a function, we always look the furthest to the right, the furthest to the left that we can go, right? And so I want to do that here using the unit circle. So I want to think about this. Y is equal to sine x, okay? So if I look at the unit circle and I am looking for the sine value is the y value. Okay, so let me just grab my unit circle. The sine value is the y value. Well, if I look, I can go all the way around this unit circle. I could pick any point on here. I could pick some obscure point, say like right here. And notice there's no open circles or undefined points as I go all the way around here, right? Any point I pick, I could easily find a defined y value, right? If I pick this random point right here, I could go over and find a defined y value, right? Same thing, I could find a random point down here and I could trace it over and find a defined y value. So no matter how far I go, I have no undefined y values, okay? So I'm going to go ahead and just say there is a y value for every point on the unit circle. So if there is a y value or a y coordinate for every point, that means our domain is negative infinity to infinity. We never have a break in coverage on those y values, right? Same thing with cosine, right? If we look at cosine, okay, now we're looking at the x value, and by the same reasoning, right? By the same reasoning, I can go from negative infinity to infinity for my x's as well, because no matter how far I go around that unit circle, I can always find a point, or there's no point, how do I say it? There's not a point where I cannot find a defined x value, okay? So we have no issues for sine and cosine. They're defined everywhere, okay? So now I'm actually going to skip tangent for a second, and I'm going to look at their reciprocals, okay? If I look at the reciprocal, okay, this is 1 over sine x, right? Cosecant is 1 over sine x. So the only issue I would have here, because this is again is still just using sine values, we know sine can be anything, but when we move any possible number into the denominator, there's only one number where we have an issue, right? And that's where this ends up equaling 0. So the bottom can't equal 0. So let's think about the places on our unit circle where we have the sine value or the y coordinate being 0. Okay, so this is going to be negative infinity to infinity, except for, so let's look on our unit circle. Where are our y values 0? Well, our y value is 0 here, right? That's at 2 pi or 0, however you want to define it, right? It's also 0 over here at pi. So anytime I land on pi or 2 pi or any extra rotations of those two, I'm going to get a y that is 0, which is going to give me a problem when that's in the denominator, right? So that means anytime I hit pi, 2 pi, or any combination of that, okay? So that goes in both positive and negative directions. That could be negative 2 pi, negative pi, 0, positive pi, positive 2 pi, and it could keep going in the positive direction, right? Anytime I land on one of these, I'm going to end up with a 0 for my sine, which gives me a 1 over 0, which is undefined, right? Because we cannot have 1 over 0, which is what all of these guys are going to give me, right? So when we talk about the domain for cosecant, it can be anything except for these specific radian measures where we get the 0 on the bottom, okay? So the same thing is true when we look at secant. Secant, remember, is the reciprocal of cosine, okay? So cosine now is on the bottom, which means it can't be 0. So I'm going to start with the domain of cosine, which is everything, all real numbers, right? Except for those that give me a 0 cosine value, right? Or a 0x coordinate. So let's get our unit circle again and look for where my x coordinate ends up being 0. So the only place on here where I end up with an x-coordinate of 0 is at 90 degrees, or pi over 2, right? I get a 0 for my x-coordinate. And down here at 3 pi's over 2, I get a 0 for my x-coordinate. So anytime I land on pi over 2, 3 pi over 2, or any extra rotations that land me on either of those in the positive or negative direction are going to be undefined for secant, because that's where I get a 0. Okay, so it's going to start in the negative direction, negative 3 pi over 2, negative pi over 2, positive pi over 2, positive 3 pi over 2, and I keep putting dots because it could be any extra rotations of any of these angle measures, okay? Because by the same reasoning, we cannot have a 1 over 0, okay? So sine can be anything, cosine can have anything. Their reciprocals can be anything except for the angle measures that give us a 0 in that denominator, okay? So let's look at our last one, which is tangent. Now, when I look at tangent, tangent is defined as my y-coordinate, right, over my x-coordinate. So if I think about this, now we have our x-coordinate on the bottom, right? So it cannot be 0. So this is one we've actually already done, because we've already seen one where the x-coordinate can't be 0, right? We get our x-coordinate from our cosine value. So tangent's domain is actually going to be the same as secant, right? Same as secant's domain, because we cannot have 0 in the denominator, okay? And then very, very similarly, right, if we look at cotangent, cotangent now has the x-coordinate on top and the y-coordinate on bottom, right? So now it's the y-coordinate that can't be 0, and where we have seen the y-coordinate not being able to be equal to 0 when we're finding domain was for cosecant, right? So I'm just going to say this is going to be the same as cosecant x, okay? All right, so last little thing is I just kind of want to give you a visual, okay? So if I want to find the range, okay, this is the domain. This is what gets plugged into the functions. If I want to look at specifically the range of just the sine and cosine functions, I'm actually going to draw a little picture down here to help, right? If we have our sine values and we have our cosine values, okay? So let's think about it on the unit circle, okay? If we're looking at it on the unit circle, okay, our sine values relate to y, right? Relate to y. So what we're really asking is how high up on the unit circle does y go, and how far down on the unit circle does y go. So here's the top of the unit circle, here's the bottom of the unit circle. Notice we're not getting any y values higher than that point, right? And we're not getting any y values lower than that point. So what are these 2 points? Well, this is our ordered pair, right? This point right here is our ordered pair 0, 1, and this is our ordered pair 0, negative 1, which tells me that all of my y values have to fall between negative 1 and 1, right? They have to be between negative 1 and 1. Or we could write this as negative 1 is less than or equal to all of our sine values, which is less than or equal to 1. Just means that they have to fall within that range. They can equal negative 1 or 1, or any number in between. okay, all possible y values. And then we look for our cosine range, or our possible outputs for cosine. It's very similar, right? This relates to the x. So now if I look at my unit circle, again, by this similar reasoning, right, then I can go, this is the point -1, 0, and this is the point 1, 0. So my x's here go from -1 to 1. They don't go any further on either side, but they could be anything in between, right? Because all these circle pieces map to x values, right, that are in between -1 and 1. So -1 and 1, or -1, all of our cosine values have to be between -1 and 1. Okay, and I'm putting that in. There will be some problems where it just says, is this a reasonable value to get for a sine value? And if they tell you it's something like 2.79, then you could say no, because it's not between -1 and 1. Okay, all right, so that is the end of section 3.3. You should now be able to finish that assignment on my math lab, and if you have any questions, please let me know.